Welcome to the Deep Dive. We focus on bringing you the key insights in AI. Now, you've probably heard about these advanced AI systems, right? The ones tackling really complex stuff, deep research, coding challenges, that sort of thing. Often, what makes them tick isn't just one big AI brain, but actually a whole team of specialized AI agents working together. But here's a thought. What if one single model could do the work of that entire team? Today, we're diving into something pretty groundbreaking called Chain of Agents, or CoA. It's research from the OPO AI agent team. They've introduced what they call Agent Foundation Models, AFMs. And the idea is, well, it's a new way for one large language model to get the power of a whole multi-agent system, all end-to-end. So our mission today is to unpack this, understand how it gets around the limits of older systems, and look at the performance, which seems pretty remarkable across different tasks. We'll explore how this single model dynamically juggles different tool agents and role-playing agents to solve tough problems. Let's get into it.
Okay, so to really get why chain of agents is significant, we should probably look at what came before. Before CoA, AI problem solving generally fell into two main camps, you could say. Each had its pros, but also some real bottlenecks.
All right, two main paths. So on one side, you had multi-agent systems, MAS. This is kind of the team approach, yeah. Multiple specialized AIs, each good at one thing, collaborating on a bigger problem. And that worked well for complex things like, say, deep research or building complicated code.
It did. Very powerful for distributing complex tasks. But these MAS frameworks had drawbacks. A big one was computational overhead. Think about a team needing constant meetings, lots of redundant communication between agents. Plus, they often needed a lot of manual prompt engineering or workflow engineering. Basically, humans had to design the whole interaction flow for every new kind of problem. And crucially, they didn't really learn well as a whole system from data. It was hard to get them to improve end-to-end based on experience.
Okay, so that's the MAS side. Powerful, but maybe a bit cumbersome, rigid.
Yeah, and resource intensive. Then the other approach was tool integrated reasoning, or TIR. This was more like a single agent, many tools idea.
Yeah.
You train one LLM to use external tools, a search engine, a calculator, whatever. It works in that think, action, observation loop. The model thinks, uses a tool, sees the result, thinks again. Frameworks like React formalize this.
That sounds more streamlined for tool use. What was the limitation there?
Well, TIR was efficient for using tools one by one, but it struggled to support the sheer variety of tools and the kind of collaborative role-playing you see in multi-agent setups. It couldn't really internally manage a team of different specialized functions or roles that activate dynamically.
Okay, I think I see the picture. You've got MAS, strong teams, but high maintenance, and TIR, lean tool users. But not really collaborative in that deep multi-role sense.
That's the gap.
And this is exactly where Chain of Agents comes in. It's trying to bridge that gap.
Right. It's aiming for the best of both worlds, but within a single model.
So like moving from that team needing constant instructions to maybe one really smart player who knows everyone's role and can run the whole play internally.
That's a good way to think about it. The core idea of CoA is enabling this complex end-to-end problem solving inside one model. It simulates the multi-agent collaboration, but it's all happening within the model's own reasoning process.
Okay, so how does it manage that, this dynamic orchestration you mentioned? If it's not external frameworks, what is it?
It's the agent foundation model itself, the AFM. It dynamically calls upon different internal capabilities, what the paper calls tool agents and role-playing agents, as part of its thinking. It's less about fixed steps and more about the model deciding, okay, now I need to act like a planner, or now I need to use the search tool.
Interesting. So it has these internal roles it can adopt. What are some of the key ones defined in the research?
Yes, exactly. They define several key role-playing agents. There's the thinking agent, which is like the main orchestrator. It manages the whole process and decides which other agent to activate. Then there's the plan agent. Its job is to break down the main query into smaller, structured steps or tasks. Also very important are the reflection agent, which does self-critique checking for errors or inconsistencies, and the verification agent, which checks the integrity of the reasoning as it goes, like an internal fact checker.
So these are like different modes of thinking within the same model.
Hmm.
But it still needs to interact with the outside world, right? Through tool agents.
It does. The tool agents handle interactions with external functions. For example, the search agent is designed to create really effective queries for search engines. It knows how to ask good questions. The crawl agent then takes over to pull specific information from web pages found by the search. And the code generate agent can write and run code in a safe environment, which is obviously key for math, logic, or data tasks.
Okay, so it combines internal reasoning roles with external tool execution. And the unique part, according to the research, it's that combination.
It is. If you look at Table 1 in their paper, they highlight this. CoA is positioned as the only approach that really integrates all four key aspects: tool integration, end-to-end execution, multi-agent collaboration, simulated internally, and data-centric optimization. Other methods might do some of these, but not all four together in one model.
And that avoids the need for all that manual workflow design.
Precisely. It reduces the communication overhead you'd get between separate agents, and crucially, it lets you train the whole thing end-to-end with data.
Okay, that makes sense conceptually. But how do you actually train a single model to be this internal team? The paper mentions a two-step process, starting with multi-agent distillation. What's that about?
Right, this is a really novel part, multi-agent distillation. The idea is to basically teach the single AFM by showing it examples of how really good external multi-agent systems solve problems. They take successful solutions called trajectories from state-of-the-art systems like O agents and distill that expertise into the AFM. It's like learning by watching the best teams play, seeing their whole sequence of actions and reasoning.
So it's learning from expert demonstrations, but from complex multi-step demonstrations. How do they generate this training data? How do they convert those team plays into something one model can learn from?
They take these successful trajectories, the whole sequence of agent interactions, the internal reasoning states, the observations from tools, and convert them into a format the CoA model can process during training. But it's not just about volume. They use what they call progressive quality filtering. They're very careful about which trajectories they use.
Filtering. Why is that so important? What are they filtering for?
Well, several things. First, complexity. They filter out simple problems, specifically ones needing fewer than 5 agent tool interactions. This forces the model to learn on genuinely complex tasks. Second, quality. They remove dirty data, things like trajectories with wrong final answers or clearly inefficient steps. They want clean, effective examples. Third, reflection enrichment. They actively look for and prioritize examples where the expert system showed self-critique or reflection. This helps teach the AFM that crucial self-correction skill. And finally, error correction upsampling. This means they give more weight to examples where the expert system initially struggled or made a mistake, but then successfully corrected it. This builds resilience.
Wow, that's quite sophisticated curation. It sounds like they're not just teaching it answers, but teaching it how to reason, reflect, and recover from errors.
That seems to be the goal. And after this distillation step, there's the second phase, agentic reinforcement learning.
Okay, RL, what's the aim here? Refining the skills learned during distillation.
Exactly. It's about further enhancing the model's problem solving by letting it learn from direct feedback, optimizing for actually succeeding at the task over the long run.
And how do they focus this RL? Is it just trying everything?
No, they use strategic data sampling again. They filter out queries that are too easy or that the model can already solve well after distillation. This focuses the RL training budget on the harder problems, the ones where coordinating tools effectively and complex reasoning really matter. Then the reward function design is tailored. For web tasks, it might be a simple correct or incorrect reward, maybe judged by another LLM. For coding or math, it's often more nuanced. They reward not just getting the right answer, like passing tests or matching a solution, but also making sure the code is formatted correctly for the tool being used.
That makes sense, rewarding both the outcome and the process. So after all this training distillation plus RL, how does it actually perform? Did Chain of Agents deliver on its promise?
The results reported are quite strong. AFMs set new state-of-the-art performance levels across almost 20 different agent benchmarks. And this is consistent across different types of tasks: web navigation, coding, mathematical reasoning.
Okay, let's break that down. What about web agent tasks? Retrieving information, navigating websites.
On the GAIA benchmark, which is known for complex multi-step reasoning, they reported a 55.3% success rate. That was a 2.1% gain over the previous best. On BrowseComp, they hit 11.1% success, which they stated was a new SOTA for models in the 32 billion parameter class. And even on a really tough academic benchmark called HLE, they achieved 18.0%.
Those numbers sound good, but can we make it more concrete? That GAIA example in the paper, the one about the architect.
Yeah.
Could you walk us through how the AFM tackled that? It seemed incredibly complex.
Sure. The query was something like, What's the architectural firm that designed a Chicago landmark named after the namesake of a city shown in a NASA picture of the day from August 2015?
Right, that's a mouthful.
It is. So the AFM, using its internal agents, would first need to break that down. The thinking agent orchestrates. It might use the search agent to find the NASA APOD for August 2015, identify the city shown, let's say it finds Marquette, Michigan, then another search for Marquette's namesake, Jacques Marquette. Next step, search for a Chicago landmark named after Jacques Marquette. That leads to the Marquette building. Finally, one more search. Who designed the Marquette building? That yields the answer. Hollibird and Roche. The AFM dynamically pieces this chain together using the right tool and reasoning step at each point to arrive at Hollibird.
That really illustrates the dynamic multi-step reasoning. Okay, impressive on web tasks. What about coding and math?
Also strong results reported there. On the AME 2025 math benchmark, they achieved a 59.8% solve rate. That's a big jump over 10.5% absolute improvement compared to previous methods cited. For coding, on Live Code Bench v5, they reported 47.9% success, and on Code Contest, 32.7%. Both are challenging benchmarks.
Can you give an example for the coding side? What kind of task shows its capability there?
Well, they describe a task involving text formatting. Imagine you have text written horizontally, like in chunks. ABC, then D, then Fig E. The task is to rewrite it vertically, but following specific, complex rules about which character goes where and filling gaps with asterisks. The AFM's code generate agent was able to produce the correct output, SDA, WAHDII. This requires understanding and executing precise formatting rules, not just basic coding.
Okay, so high performance across the board. What about efficiency? You mentioned MAS can be resource heavy. Does AFM help there?
Significantly, according to the paper, they report an 84.6% reduction in inference cost, measured by token consumption, compared to traditional multi-agent systems. And this is while achieving competitive or state-of-the-art results, so it's potentially much cheaper to run.
Better performance and lower cost. That's usually a winning combination. One more thing, generalization. Can it handle tools or situations it wasn't explicitly trained for?
They tested this. The results were interesting. The code agent model, likely because it was trained to be very strict about output formats, showed it could generalize pretty well to use unseen tools, like a visual inspector tool mentioned in the paper. It managed this by just sticking rigidly to the required format. The web agent model had a bit more trouble generalizing perfectly to unseen tools, especially with getting character-level details right. So generalization capability is there, but maybe with some nuances depending on the agent type and task precision needed.
Okay, that makes sense. And finally, they open sourced everything.
Yes, model weights, the training and evaluation code, even the training data, they've made it all publicly available, which is great for the research community.
Right. So summing up, we've looked at the AI landscape before CoA, the limitations of MAS and TIR. Then we saw how Chain of Agents aims to integrate multi-agent collaboration and tool use within a single agent foundation model. We discussed the training process, that clever multi-agent distillation and agentic RL, and we touched on the impressive performance, the efficiency gains, and the open source contribution. It really seems like a significant step.
It does feel like a refinement, moving complexity from external orchestration into the model's inherent capabilities, which leads us to a final thought for you, the listener. Think about this shift. Moving from needing an external coach and explicit team structure to having a single AI model that has internalized all those roles and can dynamically switch between them. This move towards internal, end-to-end agentic reasoning, this idea of distilled collaboration within one foundation model. How might that fundamentally change how we approach building the next generation of truly capable generalist AI systems? What new possibilities might that unlock?